Today, what we're going to do is, you look on our schedule, we're doing something called Newton's method. I am going to do that and go through it rather quickly. I want to highlight what I want you to know about it. And then we're going to get into the last section for the test today and hopefully finish most of that up. So we can have a shorter day tomorrow, spending a little bit, maybe a little bit of time on some review and recap. So today I'm going to attempt 4, 6, 4, 8. I didn't remember. The first Newton's method. This is an application, another application to derivative. And it is a clever technique designed to give an iterative set of approximations for finding root of some. So this is a so for example, that's some function. This is a root of a function. Recall a root R is just a number that you can plug in, so it's 0. So basically what it is it's a place where the function crosses the x-axis. Now here's a root, and maybe this root is important in whatever problem you need to put the numerical approximation. Newton's method is designed to do this, designed to find approximations for roots of a function. And this is why it's an application of derivative. It is terribly simple in the idea behind it. And it's terribly clever because it works extremely well. It works surprisingly well. Let me give you, or let me show you how this works. So suppose we have some function. And we want to find a root of this function right here. That's what we want to know. Now, here's the idea behind the Newton's method. You start with an initial approximation, and you run this technique, and then this technique over and over again. So, let's suppose that we guess an initial approximation of this. And you might ask, well, how can you guess an initial approximation? Well, the intermediate value theorem, right? Find some place here, plug it in, and the value of the function is -3. Find some place over here, the value of the function is positive. If the function is continuous, you have to have a root between them. Right, so there's your first. I know it's between, say, here and here. Do I agree with that? So it's positive here and negative. So let's suppose I have some initial approximation at 0. This is not correct, right? It's a little off because look, the y coordinate's way up here. It's not 0. But I get this point up here. X0. And here's the clever part. What I do is I find the tangent of this function. Now, of course, this function is not a line, it's not equal to its tangent line, but the idea is the function is sort of equal to its tangent line, close enough. And finding a root to the black thing can be positive, but finding a root to a line is easy. You can always find a root to a line, it's just linear. And I'm going to call this x1. That's my next approximation. Notice, x1 is not the root of a function, right? The root's over here, and I missed it by a little bit, right? But it's better, right? How could I make this even better? Process. So what do I do now? Find the corresponding point up here. And do the same thing. Draw the tangent line of this function. Oh, that one got really close. If you're not satisfied with this, repeat the process and just do this over and over again. From a practical point of view, Newton's method actually works incredibly well, surprisingly well, especially with sort of standard functions that you might encounter. Let me derive what happens in Newton's method. Derive this. So I'm trying to find the root here. And here is, let's say this is my nth approximation that I'm unsatisfied with. Here's xn plus 1. So I'm going to tell you what the formula is for getting n plus 1th approximation. Well, let's see. For me to get this thing, for me to figure out what this x is, this is the x-intercept of this line. So I need to find this tangent. Do I agree with that? All right, to find a tangent line, I need two things. I need a point and a slope. And there's my point, right? Everybody agree with that? It is x of n, f of x. So that's the nth approximation, and it's what? So it's that point. And I need the tangent line. And what is the slope of the tangent line at this point xn? What's the tool that we have for finding the slope of the tangent? Derivative. So it should be f prime, some crap plugged in. And what is the appropriate crap in this case? There you go. Xn. This information tells me exactly what should be y minus fxn is equal to f prime xn, because that's just a number. X minus x. So this is my tangent line. This is my dotted line. Great. What am I trying to do? I'm trying to find x-intercept. And the x-intercept should be xn plus 1 and 0. because the y coordinate at this point where it crosses the axis is 0. So plug in y equals 0 and xn plus 1 for x, and I get the following. 0 minus f xn is equal to f prime xn x minus x. Or I'm sorry, my x coordinate x. This allows me to solve for what xn plus 1 is. First thing I'll do is divide by this. And this gives me the formula. Okay, folks. There should be something that jumps out at you as a red flag here. What's something that could really mess this up? Before we close up that one. So, for example, let me give you. In practice, it's fairly rare for this to happen, but it can. So you might have some situation like this. So for example, uh, uh, use this initial approximation here. Use this initial approximation here, and this gives you x1. And it looks like the slope of the tangent is 0. So if you're so unlucky that you pick this, you go down here and pick this, then at the next form, what's going to happen? The tangent line has slope 0. And so where does it intercept the x-axis? Never. And that's why the formula explodes in your hands, right? So what would I do if I had, well, I would just change the x 0. I'd probably try to move it a little closer to this. So that's one place. Let me give you some example. Right. All right, so Newton's method is designed to find roots of a function, right? And here I asked you to find the square root of 3. Can anybody name me a function as simple as you can that radical 3 is a root of? Think of some function that you can plug in. Plug this in and you get 0. How about that? Everybody okay with it? Well, really what I'm trying to do, I'm trying to picture it. I'm trying to find this positive root. Now, you don't get something for nothing in this world, so we have to start off with a good initial approximation. Anybody want to estimate the square root? Root? Give me something easier to work with. Okay, how about that? Let's try. Seems like it's close. Well, let's see what happens. X1 is X0 minus Fx0 with F1. I'll derivative then, zero. Here, F prime of X is of course 2X. So let's, and of course, what I'm doing is I'm mimicking this through n of 0. So X1 is X0, F of X0, and that's the prime. This is 2 minus F of 2 over F prime of 2. 2 minus, see, F of 2 is going to be 1. And F prime of 2 is going to be 6. So I get 2 take away 1 6. So that's 11 6. So that's about 1.8 something. It's a little bit bigger because you gave it to me for 3 different what's it is like that. So maybe I'm not happy with this, but you can just do it again. To do this by hand, it becomes more complicated, of course. But for a computer, this is easy peasy lemon squeezy. Next problem. Well, that's the previous one, 11.6 minus F of 11.6 over F prime of 11.6, which is 11.6 minus, let's see, F of 11.6, so that's going to get square of that. So it's 136 minus 108 over 36, which is 13. 36, I guess. All over F prime, yes, which is 11/3. And let's see what I get. This is what pitch. That's going to be yeah, so this is correct to 2 decimal places, 8.734848 seconds. Actually, for a lot of simple functions like this, when you do this method, every time you iterate, it tends to double the number of correct decimal places. which is pretty good if you think about it, right? We had one here, then two here. Next time I would expect to be up four decimal places. So, um, let me do a couple of things about the square roots. Here, my function. And, now my Newton's method formula gives me this. So in this case, what it turns out to be, this is going to be x n squared minus a, and this is going to be 2x n. So I can sort of spread this out a little bit. See, notice the one x n cancels here. This is going to be minus 1/2 x n. First term like this. And then I'm going to have plus a plus 1/2 1/2 a over this. So notice this is that's 1/2 x to the n. So I get 1/2 x to the n plus a over x. This is the way I see the Babylonians used to approximate square roots. It's able to use this algorithm right here. This is the method. Okay. What I want you to understand about Newton's method is I want you to understand how it works. It's a iterative tangent function. I want you to understand that. Conceptually, I am not going to ask you to find, I'm not going to ask you on the test to find the fourth approximation. I don't want to read it. It's too easy to make a mistake doing math. I trust that you do. I want you to understand the formula and understand how it works. So let me show you kind of a bonus. Anybody know how to work the square? There's no way you can. Anybody know how to work that square root offhand? This is an ancient. Nobody does this. Let me. Here's what I'll see what square root 3 is. This algorithm looks very much like division. You don't have to take out some of this stuff. I'm not going to test you. I'm asking a second question. Break this off in sets of 2, 5, 0, 3, 11, 5, 10. Here's the way you work this out. It's similar to division, but not quite. What's the nearest square root of 3 without going over? Integer. 1. 2 is too big, because the square is 4, right? 1 squared is 1. Drop this. Okay, now you drop the next pair. You know, just like in division, when you drop the next number, next square root, you gotta drop the next 2. Now, this is where it gets a little weird. Whatever this is, double it. And leave that blank, because whatever number I'm gonna put it here, I'm gonna have to put it here. How many times does say 20 go into 200? Well, it goes 10 times, but whatever number I put here, I've got to put here. Actually, I'll save the suspense. 7, 7, and that is 189. Now subtract and drop the next pair. Do the same thing again. Double that, 34 blank. How many times is 300 going to 1100? Probably about 3. 3. 4 is going to be 9, 12, 10, 81. Drop the next pair. Double this. 346. How many times is that going to go into 8100? 3 is clearly 2, right? 3000 something. 3 times it's 2. Whatever that is, you put here. 4, 12, 6, 9, 7, 6, 1. Next pair. That's 3, 4, 6, 4. Let's see. 4, 4. That looks like it's about 3. Let's see if that works. 9, 12, 19, 13, 16. Does everybody see what I was doing? Maybe you can't like really repeat the experiment because everybody. Yeah, it's I must have subtracted it off. Like here, that's 3, 3, 4, 3. I think this is what that's 9, 12, 10. That is 81. Next pair. 3, 4, 6. 3, 4, 6 blanks. It should be twice. 4, 12, 69. 7, 6, 8, 11. Yeah, I don't know. Anyway, this is the way the algorithm works. Okay. So here's my question. Is this algorithm Newton's? Is it equivalent to Newton's? I know. Yeah, but how do you know that this is a doctrine to replicate this form? Okay, that's for sure. This one is easy to make an error, right? And also every time, look how much longer the number you get, right? And it's harder and harder to implement. But there's an important qualitative thing. Let me kind of give you a hint. This always gives the correct estimate. Notice Newton's method, what we did is the perfect approximation was like 1.8, and then it was 1.73, this. Let's suppose start off taking square root 3. Suppose your initial approximation is this. Here's the root. My initial approximation is less than 3. What can you say about the next approximation? Certainly, but compare it. Bigger or smaller? There's the next approximation. Bigger than the root. Great. What about the one after that? It's also going to be big. Every successive approximation of this method after possible approach will always give something too big if you're trying to do the positive experiment. Can you explain why that's true? So if you have any approximation here, why is the next approximation bigger than the root? The tangent line, what's the concavity of this function? It's happy, right? It's concave. That means the tangent line lies under the curve. If the tangent line is under the curve, it's got to fall short of what the root is. Right? This can't be that because this actually gives you every correct decimal place. So in particular, this thing's coming in from below. Newton's method, taking square roots, always comes in from above, and it's faster. Okay, any questions? You sometimes have to take care, Newton's method. Not only is it possible for you to hit a place where the derivative is 0 and then you've got problems, but other things can happen. So, for example, this has several roots, right? 1, 2, 3, 4, 5, 6, 7, 8. Now, what would happen, say, if I pick something reasonably close to, let's suppose that I want the root R2, and I pick something like maybe right here. Suppose I'm trying to get R2 as possible. So I pick R2 right here, and what happens? Tangent line. Almost there. So my next step is probably actually going to go to R5, isn't it? So maybe that's not a good approximation. So maybe I change it a little bit. Maybe right here, slightly different tangent line. Here. What happens next? Here, here, here. So this will probably go into R5 as well. So you have to kind of pay attention a little bit to the way your functions behave. Or for simple functions, like for example, this, or but here's another thing. Now, I can tell you what the 3 roots of this are. And f prime of x is equal to 3x² minus 3. So x equal to plus or minus 1 are critical. And minus root 3, that's 0. Right. So notice so uh, so what happens if we have okay, square root 3/5 maybe right. Something else can happen. But, yeah. Approximation. Well, x1 is equal to x0 minus f of x0. Which in this case is square root of 3/5 minus f of square root of 3/5. So if I cube this, it's going to be 3/5 square root of 3/5. That's from cubing this thing. Minus 3 times the square root of 3/5 over. Let's see, when I square 3/5, so that's going to be 9/5 minus 3/5 minus. So this is the square root of 3/5, and this is minus square root of 3/5. That's whatever's left over in this fraction. So it's going to be 3/5 minus 3, which is minus 6/5. Minus 12/5. Uh, minus 6/5. So this is the square root of 3/5 minus, that's going to be a 2. So the second approximation, if this is x0, the second one is exactly the opposite side of this. What's the second approximation? Well, this is minus square root of 3/5 minus. Well, let's see, I got to put in minus square root of 3/5. In this case, this is minus 3/5 square root of 3/5 plus 3 square root of 3/5. And in the bottom, I'm supposed to be the same thing, minus 6/5. So this is minus square root of 3/5. And I'm going to see minus square root of 3/5 again times whatever I get. So that's going to be 12/5 minus 6/5. Now this is going to be minus 2. So what happens in this one with Newton's method? Start with this approximation, and then you get this one. And then it goes back. So let's go back again. Back and forth, back and forth, forth. That's what I'm telling you. And if you go a little bit wider out, for example, like maybe right here, if you use this as an initial approximation, then the next approximation won't work. Because that tangent line go right directly to see. So it's my duty as a math guy to warn you that things can go wrong. However, again, for most simple functions, what you want to do is find a root. All you got to do is find something reasonably close. And if iterations of Newton's method appear to be sort of converging to some number, then, well, some number is reasonably close to the root that you started, then probably working out. Let me give you one more example of this. Why would you care about this? Actually, it turns out in a lot of dynamical systems models, this equation shows up in things like weather and populations, things like this. This is actually an important thing. It's the place where cosine x and y equals x intersect. And as it turns out, they only intersect in one place, basically right there. I want to find that place for cosine x and x intersect. Right, okay with that? Well, Newton's method is just made for this kind. For Newton's method, this is a little bit odd because Newton's method is designed to find roots. There are roots of a function. So here's the equation we want to approximate the solution. So solution is root f of x. Everybody agree with it? So we're looking for a root of that equation. Or of that equation, root of that function. Because remember, that's what you want to do with Newton's method. Decide to extract roots functions. So we need to write this in the proper form. So if I find a root of this, that means the x, whatever root that is, then x. Right. To use Newton's method, I need a derivative. If I agree. Okay. So let's start this bit here. Of course, we have x n plus 1, x n minus f of x over f prime of x, x n. Yep. But I need something to start me off. I need an initial approximation. Notice if I plug in 0 into this, I get 0 minus 1, I get negative, right? If I plug in 1 to this, I get 1 minus cosine 1. I don't know much, but what do I know about this? Can this number be negative? No, it can't be negative. Why? Right, the biggest cosine can ever be is 1, and the smallest can be negative 1. So this is, in fact, this is greater than 0, right? So at 0, I'm below the axis. At 1, I'm above the axis. So the root's got to be in between there. I'd much rather plug in zeros and 1s, so I'll take your suggestion. Let's just try this. See. See what happens. No. X1 is x0 minus f of x0 over f prime of x0. So in this case, that's 0. Initial one. F of xn is going to be minus 1. And f prime is going to be 1. So what's my first approximation? Well, my zeroth approximation is 0, so I guess I should start with 1, shouldn't I? Because it just gave me that. So my next approximation is going to be 1 minus f of 1. So in our case, it's going to be 1 minus cosine 1 over f prime of 1, which is 1 plus sum. And that's good enough use. But like I said, programming computer to do this is incredibly easy, right? Because it's numbers. Okay. Any questions on all that? I want you all to take away. So when you practice your Newton's method or whatever, just to get you warmed up, there'll be some problems in the book that will say like, find the first 3 approximations. That's fine, work that out, just get yourself warmed up. What I want you to do really is I want you to understand that this is a tangent line approximation. I want you to be able to tell me, okay, is the approximation going to be too small or too large? That's to do with concavity and curvature. If you remember it comes from tangent lines, then again, I think it's going to help you out right there. Does anybody have any questions? Okay. So work on this. I'm gonna give us a head start on antiderivatives. And this is, the last new piece that we have for the third exam. What is, an antiderivative? Instead of saying, what's the derivative of this? Right? So somebody remind me, what's the derivative of tangent x? Secant squared of x, right? That's the derivative. If I ask you, what's the antiderivative of secant squared x, what I'm asking you is, can you give me a function whose derivative is the said function? So you all gave me a derivative of tangent x, secant x. Can you give me an antiderivative of tangent? What's the derivative of cosine? Actually, cosine cotangent. That's a little harder. So definition. If f of x is the function of some I, we say f of x is antiderivative if f prime of x. So an antiderivative, just like I said, is a derivative in reverse, right? That is to say, if I give you the function, you've got to tell me the function whose derivative that is. Now, if I ask you to take the derivative on, there's only one answer. Antiderivatives are a little bit tricky. So let's look at the number. Anybody give me an antiderivative function whose derivative? Okay, well, you went the full 9 on that one, didn't you? Right. The first thing out of his mouth was x squared. And if you stop there, that would be right. That is an antiderivative. But his observation is this. The derivative of this is 2x for sure. But the derivative of x squared plus 1 is 2x. The other derivative of x squared plus 17. And in fact, the derivative of everything. Constant plus this. Like you need antiderivative cosine. X. Sin x will work, right? The derivative of sin is cosine. Here's the great thing about antiderivative functions. You can always check it because you all are pretty good with derivatives. Whatever you get here, you take the derivative, you get back to where you started, and you store it. Cosine is sine, pretty easy. What's the antiderivative of C? I'm not gonna tell you, but you know, this we'll talk about this later. The antiderivative of secant is the absolute, it's the natural of the absolute value of secant. See, I don't expect you to be able to figure this out. This actually requires quite a bit of focus. The point of this example is this. I could just, this could be like fake news, right? I mean, this could be a big fat lie. But it's check. So if you're a little bit skeptical of me, which maybe you should be, check it. I'll take you to the rim. Let's go through this. What is the derivative of the natural log of the absolute value of log? 1 over log. Am I done? No, I gotta multiply by the derivative of what I put inside there. And what I find inside is secant x plus tangent. Okay, so remind me, what's the derivative of secant? You guys just told me what the derivative of tangent is, secant squared. Now, notice there's a factor of C here. Somewhat. But finding it? Well, so here's the thing. Taking derivatives can be reduced to basically, you know, the chain rule is basically a sequence of steps. You can basically train anybody to take derivative. Finding antiderivatives, that's art. And I got a little bad for it. It's antiderivative of this. How about this one? X squared. Taking derivative of this is easy enough, right? Derivative of even the x squared is even the x squared. Right? How about an antiderivative? Here's a little challenge. Maybe you can take the place. Anybody can write down the antiderivative of this in terms of elementary functions, the exponential, sines, cosines, powers, roots, whatever. If you write that down in terms of elementary function in closed form, I'll give you an A in class and just walk out. It cannot be done. It was actually proven in the 1800s. You cannot write the same time. Now, that doesn't mean that it have one. It's there. And I can show you. The only problem is the function itself cannot be written. So functions, logarithms, trig functions, exponentials. You can't write it down in form. It's there. It's a function. I can draw you a picture of it. All right. And there are other ways that you can write it. When you get into 1080, you can write the antiderivative in terms of the power series, the infinite series, but you can't write it down in terms of series. This is one of the things about antiderivatives. It's more difficult, right? Writing these down, it's not always good. How about this one? Let's see. I'm going to show you how to do this right now. You're just going to have to check, make sure this is right, and that I'm not just making this up. How do you take the derivative of x log x? X log x. It's a product rule, that's right. So it's 1 times log x plus x 1 over x. Product rule minus 1. So this is log x plus 1 minus 1.
Like a formula to figure it out versus just factoring.
Well, there's sort of a large class of things that I can do to kind of help show you. There's things called new substitutions and there's integration by parts. That's going to be a big part of 1080. I'm going to show you how to do all that before we're out of it. Right? This one you can do with something called integration by parts, but I'll show you that in a second. What you can do right now, this may look mysterious. How did I get this? And it should look mysterious at this point. But what you can do is check it. And when I tell you this is what the answer is, you can say, well, I don't know if I believe you, and check it. So let's write down some simple things that we can do. So let me kind of assemble, will a rogues gallery of some antiderivatives. I'm going to give you first a theorem. If if f is some antiderivative rule f on some interval I, then any antiderivative f x is of the form f x plus c. So, for example, and in fact, Ryan pointed this out earlier, we had the most general antiderivative of 2x is x squared plus c. Let me, this is assuming that, string. Can anybody think of a function? Let's brainstorm. Can you think of a function whose derivative is 1 over x? Good, good. Can you think of something a little bit more general than just plain old log x? Right, but I mean, so what's the domain of log x? Positive x. Can you think of something whose domain is a little bit bigger? So you know that the derivative of log x, 1 over x, right? But more than that, you said log of what is also a derivative of one of x. There you go. There you go. So I would actually say this. But actually, I can, so I'm tempted to say this, but actually there's something a little bit more general. Notice for this magnetic. See here, what's the domain of this function? 1/x. Well, it just has to not be, right? It can be positive or negative. And so notice in this theorem here, you're on some interval I. Notice when you look at the domain of this, it's got 0 ripped out of the middle of it, right? And so you could actually have one constant over here, a different constant on the other side. Because if you look at the derivative of this, prime of x, this is 1/x, if x is bigger than 0, and 1/x, if x is less than 0, which is 1/x. But that's technical. If I ask you for an antiderivative of 1/x, the natural log of the absolute value is C. But this is actually a slightly more general version. Notation. You know, f of x function we often find often use this notation for the antiderivative. How many of you have seen the sign before? Seen the symbol before? This is called an integral. This is called an indefinite integral. And what it refers to is the antiderivative of f of x. Usually on some. So sometimes I will make clear when I use capital F of x, this notation is unambiguous. This always means the antiderivative. Here is a theorem. And this is kind of a cool theorem because it says the antiderivatives behave themselves. Nice. F of x, E of x have antiderivatives. But you all remember from calc from 1040 that some functions don't have derivatives, right? Or at least at some points they don't, right? It's natural to ask what functions have antiderivatives, right? I mean, there are some functions like the absolute value of x. You can't take the derivative of 0. There are some functions that you can't take the derivative anywhere. What functions have antiderivatives? Actually, it's much easier to have an antiderivative. Antiderivative, even though with that example, just because you can't write it down doesn't mean it's not nice. It's not there. It's easier. In fact, any continuous function has an antiderivative. That's not true for derivatives. There are continuous functions that, in fact, there are examples of continuous functions that don't have derivatives anywhere, but you have an antiderivative, even if it continues. In fact, one general. Then, one antiderivative of f of x plus g of x. The antiderivative of f of x plus the antiderivative of g of x. So we've got that going for us. And two, you have a constant. Right up here. So for example. Let me get kind of the roads down here. And by elementary, what I mean is just ones that are associated with functions. You might encounter. The antiderivative of somebody think function derivative is x to the n power. So when you take the derivative of the sucker, it gives you x to the n. What power should it have? If the derivative is x to the n, what should the power of the antiderivative be? And this doesn't quite work, does it? Because the power is going to be right. When I take the derivative, this will be the n power, but it'll have an extra n plus 1 in front of it, right? But I can solve that. Now the lawyers are going to make you lessons. Very, very important. What's that? N not equal to. You see, that's going to be a problem. But of course, this is far as following question. What if you equal negative 1? What if you have x minus 1 power? Well, lucky for us, the natural log of x plugs that in. I agree with that. Antiderivative of the exponential. Let's see, what if we went more general? That's gonna be something like that. I think this is quite right. You might remember what the derivative of a dx is. I know what you get. Derivative of a dx is a dx times. Remember what that is? Derivative of this is a dx times natural log of a. So just divide by natural log of a. It's just a constant to fix this. Antiderivative cosine. Okay. Antiderivative sine. I gave you this one. This one's I'll tell you what some of these are. We're going to get back to it later and see why I should put it. I think the function of derivatives. But I tell you, I bet you. What's the derivative of log of the absolute value of secant? It's 1 over secant. And then you gotta multiply by the derivative of secant, which is. So you got one over secant times secant tangent, secant's canceling it. There's a similar one. How about this? Square. Now, actually, square root of x is x to the 1/2. It's covered here. Oh, you're getting closer. Uh, there you go. It's actually the inverse of x. Remember how the derivative of the inverse t from 1 over x. I'll probably run the spirit of this. Remember this one? Inverse. And 11. So there's kind of problem. And the theorem, this theorem right here that I've got helps me kind of put things together. So if I gave you this. On the antiderivative. Well, first thing I'll do, I'm gonna take one quick extra step here. I'm gonna rewrite this. Something I can wrap my head around. All I did really is I wrote 1 over x squared, 6 minus 2 power, and square root of x as x. So let's go through this. One of the things my theorem told me is to take the antiderivative of this. All I have to do is take it piece by piece. Okay, here we got a 6 equal constant. What's the antiderivative of x to the 4? I'm sorry, x to the cube. That is x to the 4 over 4. Plus 3 x cubed over 3. This is x to the minus 1 over minus 1. This is x to the 3 halves over 3 halves. What about this piece right here? What about the 2 over x squared plus 1? There you go. How about this? But antiderivative cosine sine, right, so this is minus 4. Next. Antiderivative 3. 3x. That's 3x to the 0 power. And then something a little bit. 3 houses, 4. So it's here, minus 1 over x, plus 2/3, that's 3 halves, plus 2 inverse 10, x, minus 4, sine x, 3x. Okay, any questions? Do you remember those problems in 1040, when you first learned how to take derivatives, and they say, okay, I take a ball and I throw it with initial velocity v of this building. And they just give you these formulas, don't they? They give you squares. Antiderivative show you what this is. I'll throw a ball. Building. Height. S is 0. At velocity. V 0 up in the air. If acceleration due to gravity is minus g feet per second squared, find equation that gives find the equation. So I'm standing on the building and its height, building height S0. And here I am, and I throw this ball upwards at V0 speed per second. I've got gravity pulling on it. I want the equations of motion of this ball. And this is the first bit of magic that antiderivatives do, because this, you get these equations, you get these problem sets in 1040, and say, okay, I've got this strange equation, it's this quadratic, and you throw a ball and figure stuff out, take the derivatives, figure out this velocity, where did this come from? There's a very natural place to speak. So the acceleration at any time t, right? You all are familiar with that kind of fireside fact, right? That, well, it's an approximation, but the Earth's gravity makes this marker accelerate down at, well, actually, negative 32 feet per second. Accelerating. Close enough to constant. Okay, what is the relationship between velocity and acceleration? Acceleration is the derivative velocity. Y'all remember that? And the units kind of tell you some stuff here, because acceleration is in feet per second squared. So that's a change of velocity with respect to velocity is feet per second, change the time as feet per second squared. So if acceleration is the derivative of velocity, then velocity is the blank of acceleration. Antiderivative. And guess what? Don't let the key fool you, that's just a number. If that's the acceleration, what is the velocity? It's fall. What's the antiderivative of negative g? Remember, negative g is the number. What's it number? Right, but only my variable's not x. It's t. Plus some constant. Right, don't forget that constant. Now, actually, this thing tells me what, well, actually, let me try to see. This problem tells me what that constant is. Notice that when I start the clock on this problem, I've heaved that ball up. And this is v0. That's my initial velocity. C is v0. So I now have this equation. This equation tells me exactly what the velocity should be. Now, what I really want to know is I find the equation that gives the height above the ground. What's the relationship between position and velocity? The derivative of position is velocity. My position above the ground is measured in feet, velocity is in feet per second. So, in other words, position is the antiderivative of velocity. Do an antiderivative again, and I get S of t. Derivative of this is t squared over 2 plus another constant. Let's plug in 0 over here. And what was my initial height? S0. So now I have my improved equation. S of t is equal to minus 1/2 gt squared plus b sub 0 t. So it's familiar, like one of those things in your book. And what is, so you all know the folklore, what is the acceleration due to gravity on Earth? How many feet per second squared? Yeah, right. That's correct. That's in the metric system. In the English system, it's 32. And 1/2 of 32. You probably saw some of these ones in your homework. There's always a minus 16 t squared, right? Or if you're in the metric system, it's a minus 4.9 t squared. Right? You always see that. That's the reason for some antiderivatives to figure that out. Okay. Any questions? Here's what I want you to do tonight. I want you to look over the Newton's method, do the homework, make sure that you understand. I want you to understand this kind of big picture conceptually. But you should know the formula and be able to do one computation. I'm not going to add to the test to do this over and over again. And start looking at the antiderivatives. Bring me your questions tomorrow. We'll probably get a running start to get ready for exam 3. And without further ado,